ba 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 director. Man, what am I doing? Hello, and welcome to another exciting episode of Mr. Bell Physics. Today, we are going to be continuing our Kinematics series. This is part 3 of our Kinematics series, where today we'll be starting to talk about how to actually solve some of these kinematic problems. Now, if you're in one of my classes, you already are familiar with these lovely equations. These are the kinematic equations, and they are perhaps the most mathematically intimidating thing that we do all year. The reason why they're mathematically intimidating is because we all of a sudden go from an equation like velocity is just displacement divided by time to this. It looks a little bit more involved. There's some parentheses, there's exponents, there's a lot more variables now. There's big letters, big numbers, little numbers. It doesn't really seem like it makes a whole lot of sense. So, today's goal, walk you through it, make sure you feel good about it, and then move on with our lives. Okay? Now, the really tricky thing about kinematic equations is that technically speaking, all of these equations are correct at the same time. See, normally in physics, especially with things like forces or energy or electricity and magnetism, you are given one type of equation for one type of situation, right? Where there's always a correct time to use the equation and an incorrect time to use the equation. Not so much with kinematics. See, with kinematics, we have multiple equations that are all technically correct simultaneously. It's a big pain in the butt. But, see what I did there? But we're going to work through it. So, what I have here is an example problem. I have our formulas. We're going to work through kind of how to do it. We might do one extra problem if we have time. We'll go through it like that. The important thing to remember with kinematics is that these equations all work with a constant acceleration. Okay, if we have more than one acceleration, we have to do more than one problem. So our example problem reads, a car accelerates from rest at 2 meters per second squared. How fast is it going after 6 seconds? Now, notice we have a constant acceleration here. Okay, we know it's an acceleration because of the unit, meters per second squared. Okay, we know that whenever we see that unit, we are talking about an acceleration. But notice it is constant. It is always going to be that 2 meters per second squared for this entire time period. Velocity will change during this. Position will change during this. Time will increase during this. However, acceleration must remain constant. We'll talk about what happens when acceleration doesn't remain constant after this. So, notice we have a few new terms in our equations here. But it makes sense if you think about them. See, in our last part, we talked about what is velocity, what is acceleration. And we introduced this idea of rate of change, right? We introduced that velocity is the rate of change of position, right? So where did I start? Where did I end up? How long did it take me to get there? Whereas acceleration is our rate of change of velocity, okay? How fast did I start? How fast did I end up going? How long did it take me to get that speed increase or decrease, right? Remember, positive and negative can absolutely exist here. So when I look over here at our equations, some of these symbols aren't going to be too shocking, okay? See, instead of dealing with V, we now have VI and VF. All VI means is our initial velocity, okay? So that's initial velocity. It's the velocity that we start with. VF is final velocity. The velocity that we end at. A, as you can probably guess, is acceleration. Easy enough. If I actually spell acceleration correctly. There we go, that's close enough. T is a new unit for us, time. Okay, we've worked with it a little bit, but we'll be doing a lot more with it in the near future. And then finally, I have triangle X. What is this triangle? That triangle is the Greek letter delta. and all it means in physics is a change in. So all delta x means here is how x has changed, basically our displacement. So delta x equals displacement. It is not uncommon at all to see someone write this shorthand without the delta and just put x in there. That is totally fine. Okay? I'm going to make sure that I try to include the delta whenever possible, just to make sure that we understand that I'm not just dealing with what my initial position is, but I'm dealing with my change in position over time. Now, for units, velocity is going to be in meters per second, like it was before. Acceleration, like before, meters per second squared. Time, seconds. Displacement, meters. These aren't shocking, okay? But it does mean that we had to make sure that these are all converted into the correct units, okay? I will have a video up about unit conversions and how to do them in more detail another time, okay? It's just not on the docket for today. For our purposes, though, all of our units will be in the correct units. So unit conversions is something we'll talk about later. So let's actually start solving out this problem. So again, reading it. A car accelerates from rest at 2 meters per second squared. How fast is it going after 6 seconds? Now, I don't necessarily care what is accelerating or the scenario or anything like that. Okay, I don't care that this is a car. Okay, this could be a person, this could be a roller coaster, this could be a rocket, this could be a fish, for all I care. Okay, it doesn't make a difference. The important thing here is understanding the speed it was going, the speed it's going at now, how long it took, and the acceleration. Okay. So what I like to do for these is I like to make what I call my shopping list. Okay. I just make a list of all of my variables. And I make that list out, right, to see what I have. Okay. Because right now I'm looking at kind of word soup. And I don't know about you guys, but I'm not really that huge on soup. So I prefer kind of going through, breaking out what do I have, what do I not have, and going from there. So let's read this problem together, sentence by sentence. A car accelerates from rest. From rest is a fancy physics way of saying it's not moving yet. So if it's not moving, its rate of change of position can't be anything yet. So therefore, its initial velocity must be 0. From rest at 2 meters per second squared. 2 meters per second squared, that unit immediately tells me this is an acceleration. So I'm going to plug that right in for acceleration. 2 meters per second squared. They're asking me, how fast is it going after 6 seconds? So 6 seconds, I know that as a time. So 6 seconds. And they ask me, how fast is it going? Okay. Whenever you're trying to unpack a problem like this, look for a questioning word. How, what, when, where, why, who, something like that. Okay. How fast is it going tells me, or how fast is it going after. Okay, this after is a very important word because that tells me time has passed and now it has a new velocity. That means that at the end of that 6 seconds, my final velocity, that's what I want. Okay, so this is our unknown. Notice delta x is still unknown. Okay, delta x is still unknown at this point. But we don't necessarily need it to solve for this. Okay, let's see what we can do without it. Okay, now, like I said before, all 4 of these equations, technically speaking, are correct. And you can use any 4 of them so long as you have the right information to do so to solve. Now, right now, I have VI, VF, A, and T. So I'm going to try to ignore anything that has delta x in it. So that's equation 2, that's equation 3, that's equation 4. Okay. Equation 1, thankfully, has VF, VI, A, and T in it. Meaning it has everything that I need to solve this. Now, in a more complex problem, my general kind of rule of thumb, I like having things in this order. I go down process of elimination. I start up here. If it has the stuff I need, cool, I try to solve. If it doesn't, I move on. Because I know for a fact that one of them eventually will. Or it'll eventually give me some other piece of information that I can then use later on. Okay? A big part about kinematics is some multi-part problems sometimes. Okay? Don't be afraid of them. So, car accelerates at rest or firm rest at 2 meters per second. How fast is it going after 6 seconds? We're using equation number 1 to do this. So, I'm just going to plug in. V final, I don't know that yet. V initial, though, I know for a fact that's 0. Plus A times T, I know that's 2 times 6. So, the 0 goes away. Okay, anything plus 0 is just itself. So, it doesn't really do anything here. And I'm left with V final equals 2 times 6. In a calculator, I can do 2 times 6. Thankfully, that's simple enough math where I don't need a calculator. VF, in this case, is going to equal 12 meters per second. Okay, notice it's in meters per second because it's a velocity. So immediately, I already know the answer to that problem. 12 meters per second. Let's say now, I also asked, how far did it go? Okay, let's say what distance was traveled as well, or something like that. Okay, something along those lines. Now that I have 4 of my 5 things to solve with, things really are going to open up for me. Okay, but I'm going to show you 2 different ways that we can solve this. One that requires us to use time, and one that does not require us to use time, depending on what we actually are given. Okay, so let's start off with one that does not require us to use time. Let's say hypothetically, instead of telling us that, instead of asking how fast is it going after 6 seconds, it tells us after an unknown amount of time, the car is traveling at 12 meters per second. How far does it travel? Okay. So let's ignore t equals 6. Okay, let's ignore that. Okay, so I'm solving for delta x. That's my unknown. I have vi, I have vf, and I have a. And I'm looking through my equations. Okay, I look at equation 1. Vf, I have. Vi, I have. A, I have. T, I do not have. I cannot solve for that. Now, I could, in theory, solve for t, and then use that with any of the other equations to solve for x. That is a totally valid strategy. But I like minimizing the amount of work that I do here. So if I can get it done in one shot, I usually am going to try to. Okay, there's only really one exception of that. Okay, and that's if I want to use equation 3 to solve for t. Let's say, for example, we knew delta x, we knew vi, we knew a. We're just trying to solve for t. Okay. In that situation, you will be dealing with a quadratic, meaning you would need the quadratic formula in order to solve it. I generally recommend trying to solve for something else. Okay? Usually VF is what you will need to get out of that predicament. You could absolutely use the quadratic formula to solve that. Okay? Understand, it will give you 2 answers, one positive, one negative usually. Discard the negative one because negative time does not exist. Use the positive one. That's a fine strategy. Nothing wrong with it. But for my students, we're not as confident in our math skills all the time. Especially me, okay? True story, got C's and D's in math in my class, in my time in high school. Okay, physics is just kind of my thing. So instead, I try to look for an easier workaround. Okay? So the general rule of thumb, try to do it in one shot if you can, unless you're dealing with a quadratic, and then kind of do a little bit of a workaround. But anyways, back to the problem that we're actually working with here. Equation 2 has VF squared, we have that. VI squared, we have that. Times 2, or plus 2, we have the number 2. A, we have that. Delta x. We can solve for delta x using number 2. Let's go ahead and do it. VF is going to be 12 squared. Okay, the equation says it's squared, so therefore it's squared. Equals VI squared, 0 squared, plus 2 times A, which is 4, delta x. So, again, It looks like a lot of numbers, but I can simplify this. All right, so quick little fix here because Mr. Bell made a mistake. He originally put that acceleration here was 4 when in actuality it's 2. Okay, so quick little mistake there. Even the best make mistakes sometimes. It happens, right? But we do 2 times 2 equals 4. Both sides get divided by 4, leaving me with a final answer of 144 divided by 4, which is 36 meters. Okay, so that is how far my car has gone, assuming that is the final velocity. Now, I want to see if I can get the exact same number to prove that all these equations can be used to find the exact same answers in whatever order we want. But instead of getting rid of time, I'm going to get rid of initial velocity this time. So if I go through my equation list here, I have VI, I have A, I have T, I'm solving for X. That means that anything that has VF in it, I cannot use. So equation 1 has VF in it, can't use it. Equation 2 has VF in it, can't use it. Equation 4 has VF in it, cannot use it. Therefore, I am using equation 3. I don't have a choice. It's process of elimination. So, let's go ahead and do this. Okay, delta x, that's what I'm trying to solve for, equals VI, 0, times 6, okay, our time, plus 1/2 our acceleration of 2 times 6 squared. Now, immediately, I know that 0 times 6 is going to be 0, because 0 times anything is 0. So we just get rid of that. And then I'm left with this little mess to solve over here. Now, thankfully, this mess kind of fixes itself. 1/2 times 2, aka 2 divided by 2, it's just 1. That's going to be multiplied by 6 squared. 6 squared, when you do that in a calculator, 36. 1 times any number is just itself. So therefore, delta x equals 36 meters. Bada bing, bada boom, it all works out. Now, in a hypothetical situation where we were then told after the 6 seconds, the car then accelerates at 3 meters per second squared, or hits the brake and is now accelerating at -1 meters per second squared. The way that we would tackle that is not by really doing anything with these numbers yet, but instead by dealing with it as a whole new problem. We'd still keep these numbers in the back of our head. Like if I ask, okay, so how far did they go in total? I would need these numbers plus however far we went while we were braking, for example. And I would add those all together. But in terms of actually getting the numbers to add together, we need to do everything individually, okay, with a constant acceleration. So when in doubt, look for that constant acceleration. If the acceleration isn't constant, don't use it, okay? Break it up into pieces, okay? Sometimes that will happen, and that's okay. There's nothing wrong with that. So, with that being said, hopefully this gives you a bit of a better idea in terms of how to deal with one-dimensional kinematics. Next episode, we'll be introducing projectile motion, okay? Specifically projectile motion with no launch angle. So, until then, make sure you smash that like button. Make sure you hit that subscribe button. Make sure you hit that bell for notifications so that you know whenever I upload a brand new video. And as always, I will see you in the next video.